Let us begin to learn on states of matter. In particular, our syllabus of this chapter or this content is followed up on states of matter with respect to gaseous state, whereas the liquids and solid we have separate chapters titled under solutions and solid state. We are only concentrating on gaseous state. Let's begin with the introduction to states of matter. In general, we observe with three states of matter, that is solids, liquids and gases. Now, how do you differentiate among solids, liquids and gases is the basic criteria, or else you can say, in other words, why is matter classified into these three things? That is the basic criteria initially, followed up by gaseous state in detail. Why do we have solids, liquids and gases? First, initially we have physical properties, later on we have chemical nature or the chemical properties too. When you observe the physical properties of solid, liquid and a gas, solids when placed in a particular place will remain in that place only until and unless we pick it up or we move that, whereas liquids, they have the nature of flowing, and gases have the nature of flowing, more clearly the nature of escaping. And this is the basic difference what we observe among solids, liquids and gases. Apart from that, when we see the internal structural details or the chemical structural details of these solids, liquids and gases, you can see in the picture over here that if we take this rectangular box as a boundary line where you are placing a solid, and these might be the atoms or molecules in a solid. Similarly, this is of liquids and this is of gases. You can observe that in solids we have a compact arrangement and a definite pattern of these molecules or atoms arranged, whereas in liquids we have spaces in between them and we have a kind of irregular arrangement observed, whereas in gases lots of spaces and highly irregular. Firstly, solids have no or zero intermolecular spaces. Even if they have, that will be very little, whereas liquids have intercellular spaces and the gases, intercellular spaces or the intermolecular spaces will be large enough. We generally use the term intercellular in terms of biological sciences, and we usually go with the intermolecular spaces in case of physical sciences or the chemistry part. And the other part, most important thing, why are these molecules of a solid having so compact arrangement, is intermolecular forces of attraction. Intermolecular forces of attraction which keeps these molecules bound to each other. Here you have a lesser intermolecular forces of attraction, thereby molecules keep moving away from each other. Here we have no force of attraction, neither force of repulsion, so gaseous molecules keep on moving randomly here and there, also said to have collisions among themselves. So the basic classification over here is related with the intermolecular forces of attraction. And secondly, how are these solids converted into liquids and liquids converted to gases, or what happens when you heat a solid? Why does it convert it to liquid? When we heat a solid, what happens is spaces develop in between the molecules, and these molecular attractions will be broken. Why are these spaces developed? Because the attractive forces among these molecules of solid are broken down. Spaces will be developed gradually. A solid is converted to a liquid and then it is converted into a gas. That is the basic classification or the intro part. Now, along with these three states of matter, we also have two more states in the advanced sciences, where the two other states or the additional states of matter added to the basic three are plasma and Bohr-Einstein condensate. Where does this plasma occur? This is found among the stars, where we have excessive heat and light. because of this higher kinetic energies. Plasma is a matter containing higher kinetic energies which is usually not seen on Earth. And the next and the last state of matter is Bose-Einstein condensate, also in short named as BZ. We also abbreviate it as Becker. And what is this now? As plasma, we have seen that it is of higher energies, higher kinetic energies. Here it's quite opposite, where we have zero kinetic energies. Why zero kinetic energies is these Bohr condensates do really occur or exist at very low temperatures, and as temperature is directly proportional to kinetic energy, when you lower the temperature, kinetic energies are also lowered. Now what happens when the kinetic energies are lowered? These molecules get bind to each other, or they form aggregates, or they clump with each other, forming aggregated molecules, or the group of molecules named to be condensates. And these condensates in the name of Bohr and Einstein are said to be or named as Bohr-Einstein condensates. And now start with the main topic of ours, gases. Now, one of the most important properties of gases is a diffusion. In other words, escaping nature of gases is attributed a specific name or the technical term named to be diffusion, where a diffusion is the movement of gaseous molecules from a region of higher concentration to a region of lower concentration, which is in opposite to that of liquids, which have a property of osmosis, where molecules tend to move from lower concentration to that of higher concentration. Immediately followed by rate of diffusion. Now what do you mean by rate of diffusion? Rate of anything is with respect to time. Rate of anything is with respect to time. Here it is rate of diffusion, that means amount of the volume of gas that diffuses in unit time, where rate of diffusion is given a symbol R, and volume is given a symbol V, and time is in general given or allotted a symbol small t. Thereby R is equal to V by T. And if you have two different gases and you are supposed to calculate rates of diffusion of two different gases simultaneously, then that becomes R1 by R2 is equal to V1 by V2 into T2 by T1, because R is directly proportional to volume and inversely proportional to time. If at all we have equal volumes, V1 is equal to V2, and thereby R1 by R2 will be inversely proportional to time, and thereby we take it as a T2 by T1. The property of gases named to be effusion. Now what is effusion is, it is just similar to diffusion, and the only difference is a movement of these gaseous molecules through a small pore or a small hole. Therefore, effusion can be defined as diffusion through a small hole, in short, or movement of gases from higher concentration to that of a lower concentration through a small pore will be the exact definition. Now, you can take so many examples: a punctured tire of an automobile or a bicycle, or escaping of air from a balloon when you tie it on our birthday parties, and you have gas leakages, which is very prominent in our households. And these are the examples with respect to effusion. And now these gases or the properties of gases can be studied based on various gas laws, and in our study we have 5 gas laws described: Boyle's law, Charles' law, AVOGADRO'S law, Graham's law of diffusion, and finally Dalton's law of partial pressures. Now Boyle's law can be defined or can be stated as the pressure of a given mass of gas is inversely proportional to volume at constant temperature. The speciality of this Boyle's and Charles law is out of the three basic terms of pressure, volume and temperature, we consider two into the definition part or into the law and one is always kept constant. Here in Boyle's law, we are keeping temperature as constant and having or establishing a relation between pressure and volume. If pressure increases, volume decreases, and if volume increases, pressure decreases, vice versa. And now here, as it is inversely proportional, P proportional to 1 by V, or pressure is inversely proportional to volume, replacing proportionality symbol with a constant, PV is equal to constant, or if you want in terms of two different gases, P1 V1 will be equal to P2 V2, or P1 by P2 is equal to V2 by V1, as we have an inverse relation established between pressure and volume. Now the graphs of these gas laws are really important, where a graph of Boyle's law drawn between pressure and volume, where we always have temperature as constant, is said to be an isotherm. Graphs keeping temperature as constant is said to be isotherm. And as you can see the graph, it is known to be parabola. You can also take it as rectangular hyperbola. Similarly, a graph drawn for Boyle's law taking P on y-axis and 1 by V on x-axis is a straight line passing through origin. Here also, as temperature is constant, that is said to be an isotherm. Now the last graphical representation of Boyle's law, considering PV on y-axis and P pressure on x-axis, again temperature being constant, hence it is an isotherm, and the graph here is a straight line which is parallel to x-axis. Straight line parallel to x-axis when a graph is drawn as a PV versus P. Now moving on to the second law, Charles law, among which we have statement 1 and statement 2. That is, you can also take it as Charles law 1 and Charles law. Charles law statement 1 states that at constant pressure, for every 1 degree rise in temperature, volume rises by 1 by 273 times of its initial volume. Volume rises by 1 by 273 times of its initial volume. And that is represented as Vt is equal to, that means volume at a particular temperature T is represented as Vt is equal to V naught, that is volume at the initial point or at 0 degrees centigrade, into 1 plus T by 273, T being the next degree temperature. Charles law statement 2, where we have two cases, volume kept as constant and pressure kept as constant. In case 1, we are keeping volume as constant, thereby pressure is directly proportional to temperature. In case 2, we are keeping pressure as constant, thereby volume is directly proportional to temperature. Removing the proportionality constants, we get it as V is equal to Kt or P is equal to Kt. In case of two gases, V1 by V2 is equal to T1 by T2, or P1 by P2 is equal to T1 by T2. The graphs of Charles law statement 2, where volume or pressure is taken on y-axis and temperature is taken on x-axis, and both the cases, when you plot graphs for gases 1, 2 and 3, in either of the cases, or case 1 or case 2, graphs are straight lines passing through the origin. And in case 1, pressure is kept constant, thereby the graph, as we know, is going to be isobar. And in case of case 2, volume is kept constant, thereby the graph is said to be isochore. Isochore, volume constant. Avogadro's law, a very important law and a base behind our stoichiometry, where equal volumes of any gas or all gases contain equal number of molecules under similar conditions of temperature and pressure. That means V is proportional to N. Remove the proportionality constant and place it with a symbol. V is equal to Nk, or V by N is equal to K. In other terms, V1 by N1 is equal to V2 by N2, or V1 N2 is equal to V2 N1, where equal volumes of all gases or any gas contain equal number of molecules, and this N only is said to be our Avogadro number, our very favorite number in calculations, 6.023 into 10 to the power of 23. Avogadro's number, remember that 1 mole of any gas contains Avogadro number of molecules. 1 mole of any gas contains Avogadro number of molecules. And what is Avogadro number? Capital N is equal to 6.023 into 10 to the power of 23. 6.023 into 10 raised to the power 23. Moving on to our favorite equation, ideal gas equation, which is a combination of Boyle's law, Charles' law and Avogadro's law, where we have a combination of these three laws. We get it as PV is equal to NKT, replacing K with R, we get it as PV is equal to nRT, where N is number of moles, P is pressure, V is volume, T is temperature, and R is ideal gas constant or universal gas constant. And the values of R are said to be very important as such. Here we have the values of R in various units: joules, liter, atmosphere, calories, liter, torr, atmosphere, cc. Cc is a centimeter cube. Based on the usage of units of pressure, we take these different terms of R. And one more is, you can also convert that joules into kilojoules into by adding a multiplying factor into 10 power 3. You can also convert it into ergs by adding a multiplying factor of into 10 power 7. That is how we have the values of R. The three gas laws and ideal gas equation, we have the fourth gas law named to be Graham's law of diffusion. And Graham's law of diffusion states that the rates of diffusions are inversely proportional to the square root of densities or molecular weights. Square roots of densities or molecular weights, where we can write as R proportional to 1 by under root D, or R1 by R2 is equal to under root D2 by D1. Also will be equal to under root Vd2 by Vd1, which is also equal to under root m2 by m1. A capital M represents molecular weight, a small d represents density, and Vd is vapor densities. Now the last of gas laws, that is Dalton's law of partial pressures, where at constant temperature total pressure of a gas is the sum of partial pressures of individual gases. If we take P as total pressure and P1, P2, P3 being the partial pressures of gases 1, 2, 3, then the total pressure P will be equal to P1 plus P2 plus P3 and so on. And these partial pressures are directly proportional to mole fractions, thereby the partial pressure of a gas from total pressure can be obtained as P1 is equal to, that is partial pressure of gas 1 will be equal to total pressure of the gaseous mixture into psi 1, that is a mole fraction of that particular gas. That's not X, that is going to be psi, which is a symbol of a mole fraction. Now we have a kinetic gas equation from or formulated after kinetic molecular theory, where kinetic molecular theory is stated, or the postulates of kinetic molecular theory as follows. Molecules of gas collide with each other because they don't have intermolecular forces. During these collisions they move with rapid velocities. and because of these rapid or random velocities, their kinetic energies are really high. Velocities of each gas molecules will be different from one another, but the average velocity remains constant or same, and this kinetic energy is directly proportional to absolute temperature. These are the laws, and from these laws is formulated kinetic gas equation, which is PV is equal to 1 by 3 mnc square, where c will be the velocities and being the number of moles. And now we have types of gaseous velocities. As these during these random collisions, gases move with different velocities, and they possess each moving particle possesses, moving gas molecule possesses three kinds of velocities. That is the average velocity, most probable velocity, and root mean square velocity, or the RMS velocity. Average velocity with the symbol c bar, most probable velocity with the symbol cp, and root mean square velocity with the symbol CRMS. Now we have ratios of these three kinds of velocities possessed by gaseous molecules. Before coming to the ratio, let us see with the formula or the definition. But this most probable velocity Cp is the velocity possessed by most of the gas molecules. Velocity possessed by most of the gas molecules, and the average velocity is the average of velocities of all the gas molecules. That is sum of velocities of all gas molecules by number of gas molecules gives us a C average, or average velocity of the gas molecules. And the CRMS, as the name suggests, that is root mean square velocities. That means we have a square root of velocities, we have a mean of velocities, also we have squares of velocities. That means first each and every velocity will be squared, then summed up, then averaged, and then you have a square root. That is the meaning of RMS velocity. And these will be the formula. Most probable velocity will be taken as under root 2 RT by pi m, average velocity under root 8 RT by pi m, and RMS velocity as 3 RT by pi m. When you cancel the similar terms, what all are the similar terms present? RT, pi m, pi m, pi m. When you cancel off all these, we are left out with the square root of 2, square root of 8, and square root of 3. And the ratios of Cp, C bar, and CRMS will remain as 1 is to 1.128 is to 1.223. That means average velocity is 1.128 times of probable velocity, and RMS velocity is 1.223 times of probable velocity, or the most probable velocity. As discussed in the very first slides, there's conversions of solid to liquid and liquid to gas is because of change in the intermolecular forces of attraction and the thermal energies. These intermolecular forces of attractions are acting as a binding forces between the molecules, whereas when this thermal energy increases, that means simple heat energy increases, or when you heat a solid, what happens is intermolecular forces of energy, or the barriers of molecules being together is broken down, where this thermal energy increases, intermolecular forces of attraction decreases, and the conversions will be solid to liquid and liquid to gas. That these intermolecular forces might be forces of attraction or forces of repulsions, and these intermolecular forces, which we study in the chapters in our chemistry chapters of +1 and +2, are hydrogen bonding, dipole forces, etc. And the other one is the thermal energy is nothing